All right, next up, we're actually going to look at the ideal gas law, which actually the last equation that we had was actually a derivative of the ideal gas law. So we're working a little bit backwards, but it doesn't matter. So what the ideal gas law says is for any ideal gas, the pressure times the volume is going to be equal to the amount of moles times R, we'll figure out what that means, times temperature. So here P is in pressure. V stands for volume. N stands for moles. T stands for temperature. And of course, that one has to be in Kelvin. And actually, in this case, in these equations, all of our units have to be some specific unit. So this R is what's known as the gas constant. And in chemistry and physics, you'll find constants all over the place. They're just numbers that do not change that make the units work out, because we don't always talk in true units, so they just make units work out. So in terms of R is equal to 0.0821, and then the units are liters, atmospheres, moles, Kelvin. And so we can see those are the units of R, and so everything else must be in these units. If you are using PV equals nRT, your volume must be in liters, your pressure must be in atmospheres, your amount must be in moles, and your temperature must, of course, be in Kelvin. So let's take a look at an example of this. You have 2.3 grams of oxygen gas at 25.0 degrees Celsius in a balloon with a pressure of 5.0 atmospheres. How big is the balloon in milliliters, ml? So let's go ahead and take a look at this problem. And of course, this is another type of plug and chug type of problem. So the first thing we're going to need to identify is which equation that we use. Note that we're only given one set of each data, right? Only one pressure, only one amount, only one temperature, that kind of thing. So the equation that we're going to want to use is PV equals nRT. If we were given two of everything, then you might want to use the P1 V1 over N1 T2 is equal to, P2 V2 over N2 T2. But since we're only given one of each, we want to use this one. And so here we can plug in P is going to equal to 5 atmospheres. We, of course, know that R over here is equal to 0.0821 liters, atmospheres, moles, Kelvin. And so make sure all of our other units are in those values right there. V is what we want to solve for. And so that's what we're going to want to eventually isolate. Next up, we've got N, which is the amount. So if we think about how much gas we have 2.3 grams of oxygen gas. But of course, our units here have to be in moles. So we can go from 2.3 grams of oxygen gas. Remember, oxygen is a diatomic gas, so it's O2. And then you can calculate the molar mass. You should get about 31.998 grams per mole. And we convert that to 0.07188 moles. So we've got our N there. And then finally for T, we can see that we've got a temperature of 25 degrees Celsius. Of course, that has to be in Kelvin. So remember that Kelvin is equal to your degrees Celsius plus 273.15. So K here is equal to 25.0 plus 273.15. So K is equal to 298.15 Kelvin. All right, so now we've got all of our variables. What we're going to do next is we're going to reorganize our equation to isolate the variable that we want. In that case, this is volume. So we're going to divide both sides by P. So you've got nRT over P. And now we just start plugging things in there, right? So let's see. N was our number of moles. So we're going to go with 0.07188 moles. R is our gas constant. So 0.0821 liters atmospheres over moles Kelvin. T was our temperature. So that's 298.15 K. And then it's all divided by pressure, which was 5.0 atmospheres. And then if you think about the units, moles cancels out with moles, atmospheres cancels out with atmospheres, and then Kelvin cancels out with Kelvin. So we're left with liters. So if you do the calculations here, you'll get 0.08415 liters, only 2 sig figs here, so 0.084 liters. However, if we read the question, we want the balloon volume in ml. So one more step here, and that's to convert our liters into ml. So we have 0.084 liters. In 1 liter, there's 1,000 milliliters, and you get an answer of 84 milliliters as your final answer. So again, a type of plug and chug type of problem. You definitely want to get good at these types of problems. You'll see a lot of them in general chemistry, as well as other basics physics and engineering type classes. Again, first step, find which equation you want to use. Second step, plug in your variables, and you may have to do some kind of conversions in between, as we saw with some different units there. And then third step, solve algebraically.